In section 5.2, we talk about combinations. Before, when we talked about permutations, one of the important things was that order mattered. So now we want to talk about what happens when order doesn't matter. So let's say I have a team, maybe a working team of 4 people, and they have to pick 2 of those people to represent them at a meeting. And I want to know how many ways this can be done. So let's go through and sort of think through this problem. Right? When I'm choosing these 2 people, it doesn't matter who I choose first and who I choose second. Right? If I choose person 1 first and person 2 second to go to the meeting, versus choosing person 2 first and person 1 second to go to the meeting, then the same 2 people are going to this meeting. But we do know how to calculate out the number of ways when order matters. So maybe we can use that to help us figure out how many ways there'll be when order doesn't matter. So I want to just think about the possibilities to give us an idea of what this formula should be. So I'm going to list out all of my different possibilities. I could have 1 and 2, which if order mattered, I would think of as 2 and 1 also. Or I could do 1 and 3, or 3 and 1 if order mattered. I could have 1 and 4, which could also be represented by 4 and 1 if order mattered. Or maybe person 1 doesn't go, so person 2 could go with 3, or person 2 could go with 4. Or person 2 can't go, and then we have 3 going with 4. So if I look at what's both above the line and below the line, these are all of the ways to permute 2 out of 4. All right, so that would be my P for 2, which we've seen is 4 factorial over 2 factorial. So that should be 4 times 3 equals 12. So we can check that we got 12. But now I only want the ones where order doesn't matter. So the number of ways to choose 2 from 4, which we're going to write as C for 2. So this was when order doesn't matter. We can see is 6. So how is that 6 related to the 12 we saw before? Well, what we do is we first find all of the ones where order matters, and then I divide by the number of times each thing appears. So it's going to appear the number of ways those can be rearranged. So there was 2 options for the first one, and there was 1 option for the second one. So it's going to be this P for 2 times 1 over that 2 factorial. All right, so in general, this is going to be P n r times 1 over r factorial. So let's go ahead and put in our formula here. In general, the number of ways to choose n out of n objects, choose r, is going to be n factorial over n minus r factorial, right? That gives me the number of ways to permute them. But then I have to divide out by 1 over r factorial because now order doesn't matter. So I can put that together and I end up with n factorial over n minus r factorial times r factorial. So this gives me the number of ways to choose to choose r objects from a set of a set n. Right, so let's write that out. The number of ways to choose r objects from a set of size n. This is also written as n choose r. So the n is written on top of the r, but it's not a fraction. There's no line in the middle, and then you put it in parentheses. And both of those are pronounced N, choose R. Let's do some example problems. So we have a restaurant and it offers 15 pizza toppings. We want to know how many ways you can pick one, you can pick three, and you can pick at most three. So let's go through and look at some of these. So first, how many ways can you pick one? Well, there's 15 options, right? So we should know that the number of ways to pick one is just 15, because that's how many options there are. But let's go ahead and try to think about it these different ways to see that our formula makes sense. So I can think of it as C, there's 15 options, and I want to choose one, so I get C, 15, 1. So if I put that in my formula, that's 15 factorial over 15 minus 1 is 14 factorial times 1 factorial. Now, it's important to remember that these factorials cancel each other out really nicely. So on the top, I have 15 times 14 times 13 all the way down. At the bottom, I have 14 times 13 all the way down. And then I also have that extra 1. Right, so the 1 doesn't really make a difference, but I can cancel out everything that's left, so I end up with just 15 over 1, which is 15. So if you ever need to calculate out these factorials by hand, it's helpful to remember that they calculate. We could also just use Desmos to help us. So I can go ahead and put in here 15 factorial divided by 14 factorial. Lost a number. 15 factorial divided by 14 factorial, and I get that 15. So we can do that as well. All right, so now let's say I want to choose 3. That's going to be a more complicated example. So here we really need to use our coefficient, our binomial coefficient it's called. So I'm going to have 15 pizza toppings, and I want to choose 3 of them. So my formula tells me that's 15 factorial over 15 minus 3 is 12 factorial times 3 factorial. So I'm going to cancel the two biggest numbers. So that 15 factorial is going to be a 15, a 14, a 13. But then the 12 and below is going to cancel with that 12 factorial. But I still have a 3 factorial on the bottom there. So maybe we can write that out. And if you're trying to do this by hand, you could then maybe cancel some more stuff. So 15 divided by 3 leaves a 5 on the top. 14 divided by 2 leaves a 7 on the top. And then I have a 13. So I could just go ahead and do that 5 times 7 times 13. Oops. 13 to get my 455. Or I don't have to simplify, I can just use the calculator from the beginning. So I could have put in 15 factorial divided by 12. Let me go ahead and just put a couple factorials in here, then I'll come back, make everything make sense. So 12 factorial and then 3 factorial, and we get that 455. Just like there was a P and R button, there's also a C and R button. So another way to do this is to go into functions, and then in stats, you can find NCR, and then you just need to put in your 15, comma, 3, and it will give you that 455, right? Or you can just type NCR. You have to make that C capital. So if you type capital, lowercase n, capital C, lowercase r, you'll see that it's no longer italic. That means you've got your function, and then you can go ahead and put in your 15, comma 3. So there's lots of different ways to get this value. Okay, so now let's say we want to do at most 3. First, we have to unpack what at most 3 means. It means 0, or 1, or 2, or 3. So the biggest it's allowed to be is 3. So then I could say the number of ways to choose 0 toppings, that's C15 0. There's just one way to do that. Don't choose anything. C15 1, we already saw. That was 15. C15 2, we need to calculate. And then C15 3, we just saw, was 455. So let's see what C15 2 is. We go ahead and just change this 3 here to a 2. That's 105. So now I can add those values. 1 plus 15 plus 105 plus 455 tells me that there's 576 options. In this example, we have a group of 10 people, and we want to choose a committee from that group of 10. And the committee needs to have a chair, a vice chair, a secretary treasurer, and 4 additional people. So now, right, if I have those 7 people in my committee, and then they switch chair and vice chair, that's going to be a different committee. But if 2 of those additional people switch, that ordering doesn't really matter because I don't have special roles. So I need to sort of combine both combinations and permutations in order to solve this problem. There's actually lots of different ways we can solve it. So we're going to go through some different ways we could solve the same problem to give you some example of ways that we can think about this. So first, let's say I want to use my multiplication principle. So we want to kind of go through and just think about the number of options at each different spot. So first, maybe we choose our chair, and anyone can be the chair, so there's going to be 10 options. Next, we would choose our vice chair. Someone's already the chair, so there's only 9 people left to be the vice chair. Then we need to choose our secretary treasurer. There's 8 people left for that. And then we need to choose the 4 additional. When we're choosing this 4 additional, that's where it's a little interesting, right? So I have 7 people left, and I need to think of a way to be able to choose 4 out of that 7 where the order doesn't matter, right? That's exactly what a combination does. So the number of ways to take that 7 and choose 4 is just my C7 4. So if I multiply 10 times 9 times 8 times C7 4, then we'll get the number of ways to choose this committee. And that turns out that that's going to be 25,200. You can check that on a calculator or on Desmos. Okay, so let's try a different way. Let's say that I'm not going to use my multiplication principle. I'm just going to think about this in terms of permutations and combinations. So first I can pick, so step 1, pick the chair, the vice chair, and the secretary treasurer. So here, order matters. So I want to use a permutation. So I'm going to take my group of size 10. I'm going to take those 3 people in a way that order matters. So I get the number of ways of doing that is P 10, 3. And then step 2, we're going to pick the extra 4, the bonus 4 people. So now I've already picked 3, so I have 7 people left to pick that 4, but here order doesn't matter, so I'm going to give a combination. So overall, I get my P10 3 times C7 4, which we can again calculate out, and we'll see that's still going to give us that 25,200. Right, so the point of this is that there's lots of different ways to go ahead and calculate these out. There was no reason why I had to pick the chair, vice chair, and secretary treasurer first. I could have first picked the extra 4 people, pick who gets to be those members of the committee who aren't one of the named positions. But to do that, I now have my entire 10 people, and I'm choosing 4 from that group. And then after I do that, step 2, I'm going to pick the chair, the vice chair, and the secretary treasurer. So that's going to be here, order matters. P10, nope, not 10 anymore. I've already picked 4. So there's only 6 people left. And I have to pick 3 out of them. So in this case, I end up with C10-4 times P63. And that will again be 25,200. So there's lots of different ways we can do this. Let's do one final way. So in my last way, the first thing I'm going to do is actually pick all 7 people who are going to be, so step 1 here, pick all 7 people that are going to be in the committee. So the number of ways to do that, I'm going to say order doesn't matter. So I'm going to have C, there's 10 total people, and I'm going to pick 7. And then out of those 7 I choose, out of the chosen 7, pick 3 for the chair, the vice chair, and the secretary treasurer. Now, whoever I pick first will become the chair, second will become the vice chair, and third will become the secretary treasurer. So here order matters. So I'm going to use a permutation instead of a combination. Out of those 7, I'm going to pick which 3 I want to be my positions. So in this case, I'm going to get C 10-7 times P 7-3. And that will also give me 25,200. So there's lots of different ways of thinking about these problems, but they all give us that same answer.